All right. Good morning, everybody. Welcome back. So let's pick up where we left on Monday. Okay. Just don't forget that you have lab today. So for those of you that have online labs, just join the online section, right? And the ones that have in person, just join Glenn's section. Okay. Okay, so let's share my screen here. Okay, so that's where we stopped on Monday. So I showed you the difference between physical properties and chemical property. Okay, so every time you have a physical property or a physical transformation, that's going to be something that happens without producing new compounds. Okay, so look at the whole system at the beginning and the whole system at the end. No new compounds produced. That means a physical transformation or a physical property. And the chemical transformation or chemical property is the exactly opposite. Okay, so if you compare start and end, you are going to see that new compounds were produced. And the examples I gave you for physical property was boiling point and chemical property flammability. Okay, now let me show you physical changes and chemical changes. Again, it's the same idea. Physical change is any change that does not produce new compounds. And chemical change is any change that produces new compounds. Always, always, always look at the whole system in the beginning and the whole system in the end, compare both, and then you are going to be able to classify physical change or a chemical change. All right, so let's do a practice here. In the containers below, the green spheres represent atoms of one element, and the pink spheres, the atoms of a second element. In each case, the pictures show either a physical or chemical change. Identify the type of change. Okay, so for A, B, and C, identify if it is a physical change or chemical change. Okay, let's give you a couple minutes to think about the problem, and then I will solve with you guys. Okay, so let's see. Most of you are saying we have physical, chemical, and chemical change. Let's see. Okay, so seems like we can solve the problem. Okay, so let me switch. to the other screen. Okay, so I think there is no secret here. So let's just solve together and see if you guys got the right or the wrong answer. Okay, so just to represent as a sort of chemical equation, I'm going to call the green spheres as an element A and the pink one as an element B. Okay, so for the first transformation, we started with A bonded to B. So let's represent like that. And after the arrow, so after the transformation, we still have A bonded to B. So let's represent the product as still A bonded to B. Looking the start and the end, you have exactly the same compound. No new compounds were produced. Therefore, you are right. This is a physical transformation. Okay. Yes, John, probably it was heated up. Yes, you are right. Okay, so here you have them all together, and to split them up, you have to provide energy, and then they start moving with higher speed. Okay, so now let's take a look at B. So again, B started with atom A bonded to atom B. So that's what we have in the initial system. And after the transformation, now we have A bonded to A. So A bonded to A is represented as A index 2 and B bonded to B, B2. Okay. So every time you have an atom bonded to itself, we are going to use the index. Looking at the beginning and at the end, we can clearly see here that we produced new compounds, and therefore we have a chemical transformation. So far, so good. And then finally, C, we started with A bonded to A and B by itself. After the transformation, we have ABA that you can represent as A2B. And it's always the same thing here, guys. There is no mystery. Look at what you have at the beginning, and then what you have at the end. Compare both. New compounds produced, therefore a chemical transformation. Yes, John, you are right. So I'm not worried regarding the balancing of the equation for now. But yes, you have 1, 2, 3, A2B. Okay. So don't worry about balancing the transformation for now. Okay. Okay. So this is the secret to classify a physical property or a physical transformation or anything that's physical or chemical. Always look for changing in the composition before and after. Okay, very good, very good. So let's go back to the PowerPoint. All right, so let's talk a little bit about mixtures and classes of matter. Okay. So very simple here. Use your common sense. We have we started here with everything, and we ask whatever we have, can it be separated by a physical process? If the answer is no, then that means you have a pure substance, okay? For example, if you just have water, that's a pure substance. Once you establish that's a pure substance, then you are going to ask if can it be decomposed by a chemical reaction. If the answer is no, then you have an element. If the answer is yes, you have a compound. Okay, so the trick to classify as an element or a compound is very simple here. Element is composed by just one type of element. For example, pure gold is composed only by gold. You don't have another element in the composition. Water, on the other hand, is composed by hydrogen and oxygen, so two different elements, and that means water is a compound, okay? Okay, now let's go to the right side of the chart here. If what you have can be separated by a physical process, then you have a mixture, okay? A mixture, you have more than one compound or one compound and one element, something that's just not one compound or one element. Once you establish that this is a mixture, then the next question is it uniform throughout? Uniform means that you only see one phase. If it is yes, then that's a homogeneous mixture. For example, vinegar. If you see more than one phase, then that's going to be classified as a heterogeneous mixture. For example, here a salad dressing. You can clearly see here one phase on the top, another phase here at the bottom. So therefore, it is heterogeneous. Okay. So again, here use the common sense and use the chart if needed. Okay, so let's think about two examples here. Okay, so first system that we have, it's water and a little bit of salt, and that's the picture of our system. And second system, we have water plus sand, and here is the picture of our system. I want you guys to think about how you can classify this system. Is it a pure substance or mixture? If it is a mixture, is homogeneous or heterogeneous? If it is a pure substance, is it an element or a compound? Okay, so let's think about that for a minute or two. You don't need to answer me if you don't want, and then we will solve the problem together. Okay, so again here, it's common sense a little bit. Water plus salt, uh, that's a system that has two compounds, so therefore it is a mixture, okay? And once you establish that it is a mixture, if you only see one phase, one clear phase, that means it's a homogeneous mixture. Okay, so water plus salt, homogeneous mixture. And water plus sand, again, you have two compounds here. So therefore it has to be a mixture. You see two phases, therefore a heterogeneous mixture. Okay, so there is no secret here, guys. Just it's visual, basically. Okay, so just look at the system, use your common sense, and there is there will not be any problems for you to solve uh, any of the questions that I would throw on your way. Okay, moving on here. Now let's talk a little bit about separation techniques. Separation techniques are used to isolate one or more components in a mixture, okay? So there is no point to use a separation technique if you don't have a mixture. And again, two types of separation techniques, physical and chemical. And guess what? Physical separation techniques, a new compound is not produced during the separation process. Okay, so you start with a composition and you finish with the same composition. For example, filtration in a chemical separation technique is exactly the opposite. A new compound is produced during the separation process. Okay, you start with the composition and you finish with a different composition. And two examples that I like to talk about for physical separation technique, filtration, chemical separation technique, precipitation. Okay, so let's talk a little bit more about those two examples. Okay, so let's start with um, filtration. Okay, and let's use our water plus sand example. So we have here water, and at the bottom, we have sand. Filtration is a very simple process. So we are going to filter our sample through a funnel. So when the sample is filtered, you're going to collect uh, pure water at the bottom, and you're going to trap the sand in the funnel. Okay, so the secret here is to look at the whole system at the beginning and at the end. Okay, so here we have everything at the beginning, water, whoops, and sand, and look at everything at the end. You will still have water and sand. Okay, so it doesn't matter that they are in different flasks. You need to look at the whole thing. The composition was not changed, so therefore this is a physical separation technique. when you have, for example, precipitation, that's going to be a chemical separation technique because new compounds will be produced. Okay. So for example, here, you don't need to know this at this point, but that will make a good example. If you have water, sodium plus, and Cl minus in solution, if you add silver plus to the system, at the end, you are still going to have water, sodium plus, and you will get a solid. And the composition of the solid is AgCl. Okay. So look at the beginning, look at the start. You have water, you have sodium plus, Cl minus, and silver plus. Now look at the end. You still have water, still have sodium plus, but now you have a compound that was not present before, AgCl. Okay? So just the fact that you produced a new compound, that means this is a chemical transformation. Okay? Okay, very good. Let's keep going. Go back to the PowerPoint. Okay, very good. Let's talk about the scientific method. Okay, so everybody in the scientific field should know the scientific method and how it works. As a scientist, you are always observing nature. And your goal is to decipher one transformation in nature or a phenomena that happens in nature. Okay, so you're always observing the whole system. In your observations, you are going to perform experiments, okay, using a small sample of your observation. Those experiments will provide you with data. So collecting good data is very, very important. With this information, then you are going to identify a pattern. Okay. So nature always have a pattern. With that, you are going to establish a law and propose an explanation to what you have observed. And that's going to be your hypothesis. Okay, so attention here, all this process here to go all the way to your hypothesis, you gotta do experiments in the lab, okay? So cannot collect data from the opinion of your neighbor or your uncle. So that's not scientific. Once you have your hypothesis, you are going to do new experiments. And if those new experiments confirm your hypothesis, then you have a theory. If not, then you have to go back and improve your hypothesis. Once your theory is verified by other people, then you have a model. Attention here, guys. A scientific theory or scientific model is never, ever perfect. Okay. Science is in constant transformation. At some point, someone we will do an experiment that your model or your theory is not good for that. And when that happens, your model needs to be improved. So we are always looking for a better model or a better theory. A good theory or model must be able to predict and explain future experiments. That's the main characteristic of a good theory or a good model. All right. So as I told you, collecting data and recording data is very, very, very important. And we are going to focus our attention to that from now on. So let's start with the definitions of accuracy and precision. Accuracy means that the values obtained experimentally are close to the expected, while precision, the values obtained experimentally are close to each other. This does not mean they are accurate. Okay, so there is a huge difference between accuracy and precision. Accuracy, what you obtained experimentally, are close to the expected. Precision means that all the values are close to each other. This does not mean they are accurate. Okay, just a second here. Let me switch my screen really quick. Okay, so let's tackle here 4 examples, and hopefully it will be more clear for you the difference between accuracy and precision. Okay, so we have here someone throwing darts. The goal when you throw a dart is to hit the center of the circle, right? The bullseye. Okay, so the bullseye will be our accuracy. So let's see here the first person threw a bunch of darts. Can you see here that all the darts hit the bullseye? So all the values obtained experimentally are close to the expected. So this person has accuracy. Now, the second question is this person precise? If all the values are close to each other, not scattered, the person is precise. See here, all the darts are right at the center. So that means this person is accurate and there is also precision. Now let's take a look at the second person here. So the second person got all the darts in a very compact region here, but far from the bullseye. Now, all the values are far from what was expected. So therefore, there is no accuracy. But is this person precise? Yes, this person is very consistent in being not accurate, right? So all the darts in a very small and compact region. So there is a lot of precision. Now let's take a look at the third person here. So the darts are more scattered, but they are fairly close to the bullseye. Okay. So first question here is this person accurate? Are the expected values close to what was expected? This person is pretty accurate. So there is a good accuracy here. However, all the darts are kind of scattered, so they are not close to each other. So therefore, there is no precision. Okay, see the difference between accuracy and precision. Sometimes we think they are the same, but they are completely different concepts. And the last person, boy, oh boy. Ay, ay, ay. This is bad, right? So nothing here. No accuracy, no precision. All scattered, far from the center, bad. Yes, Brody. I throw like the last one as well. Sometimes like even outside here, it's really not accurate nor precise. Okay, so let's take a look at a second example just to make sure we understood the concept. So let's work with numbers now. So you go to the lab in 2 weeks and you perform an experiment and Glenn expects you to get 15.4 as your result, okay? So student number one collects, do 3 trials, collects 20, 19.6, and 19.8. Student two, 21, 10.5, 18.3, and student three, 15, 15.3, 15.6. So what I want you to think about is to classify each student as accurate and precise. Okay, so let's take a minute to think about that, and then we will solve together. Okay, seems that it's very clear for everybody, which is good. So we can move on a little faster. Okay, so this is, oops, the benchmark for accuracy. Student one is way far from the expected, so there is no accuracy here. However, the values are very close to each other, which means there is precision. Okay, so no accuracy, but yes, precision. Student two is all over the place, far from the expected, so no accuracy, no precision as well. And student three has to be the example that everything works, right? So very close to the expected, values are close to each other. It's the perfect student here. So there is accuracy and there is precision for student number three. Okay, is the concept of accuracy and precision clear to everybody? So I think so. You guys were able to solve the problem here. Okay, very good. So let me see here what we have next. Okay, so let me switch back to PowerPoint. All right. Okay, so let's talk about significant figures. Okay, so I want you to really pay attention to the rules here. It might be confusing a little bit in some cases. It takes practice. We are going to practice a lot, and you are going to be able to tell the sig figures for any number that I throw your way. Okay, significant figures indicates the confidence or precision which a scientist states a quantity. Okay, more sig figures we have, more confidence in that measurement. Okay, let's take here a simple example. We have here a pencil, and we would like to measure the length of the pencil. The first ruler has 1 unit increments. Okay, so we can say for sure that we have the length of the pencil is between 8 and 9, so closer to 8. But can you tell the decimal using this ruler? You cannot say for sure, but you can estimate. For example, here I would say maybe 8.5. Okay, so you can for sure is 8, maybe 8.5. So you have 2 digits expressing your result. Now let's take another ruler, and we have 0.5 increments now. Now for sure, I can say that, oh man, this, I would say 8.5 for sure. Maybe move a little bit out here, maybe 8.52. Okay, so see here that using a different ruler, now we can say for sure is 8.5, and we can estimate the third digit. So we are providing more digits to the measurement, more significant figures. That means we are increasing the confidence or precision of our measurement. Pay attention to the rules to count the significant figures. First one, zeros at the beginning of a value are never significant. Attention to the second one. Zeros at the end of a value and after a decimal point are always significant. Okay, we must have the decimal point for those zeros to be significant. Third rule, zeros between non-zero digits are always significant. And fourth rule, zeros at the end of a value may or may not be significant. If there is no decimal point, then they are not significant. If there is a decimal point, then they are significant. All right, so let's follow those rules, and that will cover all the examples in which we need to count significant figures in a number. Okay, so the goal here is to look at the number and determine, okay, this number has 2 significant figures or 1 significant figure or 4 significant figures. Okay, and I want to get this example solved, and then we can finish for today. Okay, so we need to finish this example. Okay, let's think about the example for a minute. Okay, so I want to count the number of significant figures for each number, and then I will do with you. Okay, so just follow the rules, pay attention, careful with the zeros and where they are at, and then we will go from there. Switch here. All right, very good. So let's start with 4.803. Okay, so the rule here is always start from left and move towards the right side of the number. The very first sig figure that you're going to start counting is any digit that is a non-zero digit. So we start left. We have here the number 4. So that's a number different from 0. Then yes, that's a sig figure. And we are going to start counting towards the right side. So after the 4, attention here, we have a decimal point. Next digit is 8. So that's a non-zero digit. We will count. Then here we have a 0. This 0 digit is in between two non-zero digits. Therefore, it is always significant and also is after a decimal point. So we are going to count the 0 as a sig figure. And finally, 3, a non-zero digit that's also significant. So therefore, here we have 4 sig figs. Okay, second example, 0.00661. Always look left, move towards your right. So the first digit is a 0. So that's not going to be counted. After the 0, we have another 0, not going to be counted as well. Another 0, not going to be counted. Finally, our first digit that's a non-zero is 6. So we are going to start counting from there. Another 6, also significant, and 1, also significant. Okay, so therefore we have 3 sig figs. And C, very similar, 0.0300. Always look left. 0, not significant. Another 0 here, not significant. 3, that's our first sig figure. After the 3, we have a 0. And this 0 is after the decimal point and after a non-zero digit. Therefore, it is significant. And the last 0 is also significant. Therefore, 3 sig figs. Just give me 1 minute and I will finish the last one here and you guys can go, okay? 300. Always look left, move towards the right. First digit is a non-zero, so therefore it is significant. After this digit, we have a 0. If we don't have a decimal point right here after the last 0, that means this guy here is not significant, and this one is not significant as well. Okay, so therefore we have just one sig figure. Very careful with that, guys. If we had a decimal point here, just the fact that this decimal point is here, we would have to count everything after the 3. Okay, so the decimal point indicates that we have confidence that this is a 0. Okay, so thank you very much. Sorry to extend the class. Hope you have a good day, and I will see you back on Friday. Bye-bye.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.